First of all, hello everyone. I'm really glad that you attend this talk. Thank you very much. Also, big thanks to organizers, of course, and Gosim Spotlight team. It's really nice to be here and speak to you today. So, I'm really passionate about performance engineering, and Rust is really great language for that kind of work. But there is one thing that's still challenging in any language, like no matter what language you will use. Benchmarking is it's hard. And today I'll introduce you to a new way of benchmarking named paired benchmarking and a open source library Tango that I wrote that implements this idea in Rust. So let's start with very simple basic concept. How do we measure performance today? The idea is very simple. You have algorithm, you repeat it a bunch of times in a loop, and then using some high precision system timer, you measure the time that this loop takes. That's it. You can do a lot of things on top of that, like you can measure mean, median, you can build confidence intervals, but the main issue I have with this approach is the assumption that performance will stay the same when you execute algorithm multiple times. And this is so wrong. There are a lot of reasons why we cannot measure performance precisely. I cannot go through all of them, but important thing is that those factors that influence performance, they span multiple system levels. It's hardware, it's operating system, it's runtime, and Rust still has very little bit, but still has runtime, like for example, allocator state, right? And all this leads to a lot of silly situations when you cannot actually it feels like you're chasing the ghosts. You're trying to measure some performance, you see difference, but now it's not there again. What's happening, right? So how do we tackle this challenge today? How we try to approach it? Well, today the approach is very simple conceptually. You control what you can. You randomize everything else. And you can do a lot of meaningful work using this approach. And frankly speaking, it's the only one. So the question is, can we do better? And yes, I believe we can. And better solution, I believe, is never run single algorithm in isolation. You always need to run two algorithms you want to compare on the same hardware at the same time simultaneously. This way, if computer has some kind of biases, those biases will influence both algorithms at the same time. And when you subtract one time from the other one, most of the common mode bias or common mode noise will be eliminated. So let me illustrate the point. So here you see two runs of some algorithm. It doesn't really matter what it is exactly. But those two runs were taken, obviously same hardware, same everything, but it was several seconds apart, right? As you see, they don't look like each other, right? They kind of different. But if you will take samples that were close to each other, like for example, if you will plot all odd samples against all even samples, right? You will see something like that actually on a short-term scale, performance is very predictable, right? And even in situations where when we have some fluctuation, like blue line is a difference, right? So even in situation like here, you don't see my marking, never mind. So even in situations when performance is different, it is symmetrical. And it is important because it tells us that the source of this bias, it doesn't come from the algorithm itself, it's the environment. And it allows us to reason about performance and more specifically about outliers more rigorously. So one takeaway from this is, performance is like weather, I would say. So it's pretty trivial to predict how weather will look like in 15 minutes. Well, Dutch people will probably tell you that it's impossible here in Netherlands, but you get the point. It's much easier than to predict how it will look like in a month, for example. So we need to leverage this fact somehow. And this is what Tango designed to do exactly, right? How does it work? Well, you build two executables out of your project. You don't have to build them at the same time. But when you run benchmarks, you need to have them both at hand, right? Usually, those binaries are built from different branches from your version control system, but, well, not necessarily. For example, it might be the same branch, but with different compiler options or different, I don't know, like different libraries, versions of libraries, right? Each binary contains, well, your benchmarks and the runner itself. And the trick here is that on all major platforms like macOS, Windows, Linux, each executable is actually a hidden dynamically load library. So it's like DLL or SO or dilib. You can treat each executable as dynamically load library. So what it allows the runner to do, like it can load both binaries into same address space and orchestrate benchmarks in a way that they will be run simultaneously. There are some tricks to it, but anyway. So I think I have time to do a demo of how it works in practice, right? Do I? Yeah, 4 minutes is it's plenty. So let's do that. And to do that, I will mirror. Okay, so you see my screen, right? Let me make it a little bit bigger. So I pre-built, first of all, benchmark. I have a very simple benchmark. What I'm doing is I'm generating 1 million numbers, random numbers, right? And then I, iterating over them, add 1 to each number, and then sums it. That's it. Very simple benchmark. What I will compare it to is to adding 2 to this number. In both cases, it's immediate value, right? Nothing, like, no magic here. So I pre-built those binaries just to save on time, right? There are 2 of them, sum plus 1, sum plus 2. So what I will do right now is I will run, let's run sum plus 2 and compare it to sum plus 1. I will give some options additional. I will explain it afterwards if you're interested. So let's see what's happening. So, let me make it a little bit smaller, like that. So we see 0.5% difference, but it might be a fluke. Everybody knows that, well, it's very small difference, right? So let's run it one more time. Well, it's still there. Let me actually run it in for loop in bash, just to run it like 10 times, for example, 10 times, like that. Done. And I will decrease time from like 1 second to 0.5 second, just to make sure that the difference is stable. We can actually check, like we can swap benchmarks, right? To make sure that this is not like some kind of bias. So let's compare sum plus 1 with sum plus 2. We should have approximately 0.5% of speed up, right? Because like we're just changing to benchmarks. So you see, guys, how precisely we can measure performance if we really like build the measurement right. So this is my demo. So let me go back to slides real quick. How should I do it? Like that, probably. Yeah. Okay, so the outcome is that computers were really never designed to reproduce the performance. They were built to reproduce the results of computations, not the performance, right? But in order to like build the measurement right and run benchmarks in the right way, we can actually benchmark performance more stable and in more noisy environments, right? And this is, I believe, very important today in the context of cloud, for example. A lot of code is run in the cloud. So this is it for me. Thank you very much. I invite you to try it out. Like there's QR code to a project page. Try it how it works for you, how it fits your workflow, and share your feedback. Thank you very much and happy benchmarking.